All right, so we are going to pick up where we left off last time, and we were talking about calorimetry. We were able to determine specific heats of unknown substances, and we can use calorimetry to also determine heats of vaporization and heats of fusion, and in turn identify unknown substances. On the screen are all the Bozeman videos. This link is on your Edline page, and everything is clumped together by Big Idea. And we're in the thermodynamic Big Idea, which is 5. I'm going to show you a few pieces of things that I think will be helpful to you. And I do highly recommend that you take a look at some of these initial videos. I'm going to show a few of these at the end as well. But not from start to finish because it's too long. In regard to calorimetry, we're going to take a look. We already did the first part, but it'll serve as a good review, and then we'll pick up with the second piece of it now. We'll also be calculating changes in enthalpy using Hess's law. This is a little different than what we talked about last time, but it's not difficult if you're good at algebra. And then we'll be starting 17 as well and putting the pieces together. I have a second Pogel packet for you that goes over some very basic terms, and I think it'll be helpful to you. Yeah?
Are we just going to Hess's law today, or are we going to go past?
We're going to go a little bit past so that I leave Friday with just half, and then practice and the practice quiz and all that, because I want to run the lab on Wednesday. We're going to make hand warmers. Your quiz will be a week from Monday.
Just in chapter 6?
6 and 17. Yeah, they are married. They go together.
Did we learn anything in 17 last year?
Say it again?
Did we learn anything in 17 last year?
A whole lot.
Oh, so it's a
You
lot.
learned entropy, free energy, thermodynamically favorable, a lot of review. All right. We're going to take a look at a few things here.
Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 51. It's on calorimetry. And like anything in chemistry, a lot of this can go back to Antoine Lavoisier, that brilliant chemist who started a lot of modern chemistry. And so calorimetry, if we just break down that word, it means the measuring of heat. And the first calorimeter that was created by Lavoisier was an ice calorimeter. And basically what you had was a chamber that had ice on the inside, and then an insulating chamber of ice around the outside of that. And then you would put something inside the calorimeter, a candle for example, and what would happen is it would generate heat as it's doing combustion. It would melt the ice around it, that ice would turn into a liquid which you could measure. So you could measure the amount of energy that's being released from the candle. He then put something living inside there. He used a guinea pig to start. And what he found is that it occurred in the same way. In other words, that guinea pig is doing respiration, which is a form of combustion. It's using oxygen, it's releasing heat. And he showed that this is essentially the same kind of a process. Requires oxygen, gives off carbon dioxide. And so what he was really looking at is the energy given off by this system. And so a calorimeter is pretty simple. It only has 2 parts. It has a heat bath around the outside. And that generally is made of water, because we know specifically how water changes over time. And then you're going to have a chemical system that's placed inside of that. We need a thermometer inside that heat bath so we can measure what's happening as we get changes of energy within it. And so we can measure energy change from that chemical system. We could use this to measure everything we described in the last video. The specific heat capacity, the enthalpy of fusion and vaporization, and also the enthalpy of the reaction. And so let's start with water. Imagine that we have a
And so this is what we talked about last time, where you have Q is equal to MC delta T. Be careful here. This is a funky unit for specific heat. Specific heat should be a C, and I believe this is a typo. The Q should be here.
Beaker of water, and we're adding energy to that. Remember, we measure how easily it's heated or cooled using a measurement called specific heat. And so if we break down that equation, specific heat is equal to the quantity of heat transferred, and we're going to measure that in joules, divided by the grams of the substance, in other words, how much we have, times the temperature change. And so let's give you a real example, because we know specifically what the specific heat is of water. It's 4.18 joules per gram Kelvin. And that's been well established. It's going to be important that we understand that as we start to do some calculations related to calorimetry. And so imagine we have 250 milliliters of water. Now what's interesting about water is we know immediately that we have 250 grams of water. And we started at 18 degrees Celsius. And so our mass is 250 grams, and our initial temperature is going to be 18 degrees Celsius. And let's say we heat it up. And so over time it changes, and at the end it's 65 degrees Celsius. And so our final, our T sub F is going to be 60.
How do we calculate the change in temperature? Final minus initial, right?
65 degrees Celsius. And so what we can do is figure out how much energy was added to that water. And we're going to use specific heat to do it. Again, specific heat is equal to the quantity of heat.
I'm going to forge ahead a little bit because they're just plugging and
The quantity of
checking.
heat that was transferred is 4.91 times 10 to the 4th joules. And so where did that energy come from? It came from the heating of that water. And so if we know how much the water changes in its temperature and we know its mass, then we can figure out how much energy is released. And that's really how a calorimeter works. All you have is you're going to have a vessel where we're going to have that reaction or that heating or that phase change occur. And then we're just going to have it sitting inside this heat bath. We can measure the changes in temperature. And by measuring the changes in temperature of the water, we know how much energy is being released from that vessel.
All right, let's slide ahead again.
Enthalpy of fusion, that's when we're going, remember, from a solid to a liquid or backwards. We can measure enthalpy of vaporization as we're going from a liquid to a gas, or we can just measure that enthalpy of reaction. We can measure endothermic and exothermic reactions. And so that's the role of a calorimeter. And so could you design or interpret the results of an experiment? Again, what we're looking at is changes in the water, and then we can work backwards to figure out how are those changes coming from that vessel, and I hope that was helpful.
And this is one of the things that they would expect that you can do, and we'll get into that more with the hand warmer lab. But like I said, if you've never seen any of these Bozeman videos, you've done yourself a tremendous disservice. They will help you understand concepts a lot better. The one with temperature also is very good. We'll come back to that in terms of molecular motion, and we'll get into entropy today, which is a measure of disorder in the system. The bond length and bond energy, we covered that concept when we were drying compounds, and that was assessed on your semester exam. So again, this will help you if you have a lot of concepts in your mind and you feel like they're all jumbled. I think that's where the videos will really come into play. They won't necessarily help you with the math, but they'll be very beneficial for concepts. All right, so this is where we left off last time. And now what we want to look at is energy changes that accompany a change in state. So when you undergo some type of physical change, for example, solid to liquid melting or liquid to gas vaporizing. And when these substances undergo these types of changes, heat is still transferred. Now, if you just worked off Q is equal to MC delta T, you would have a problem here. So previously, when we were calculating heat transfer, we said, all right, well, Q is equal to MC delta T. However, what's the change in temperature during a phase change? 0. So what would Q be? 0. But heat is transferred during a phase change, so we need a different formula to calculate heat transfer during a change in phase. And that's what's illustrated here. So we know vaporization is the change from liquid to gas. Heat of vaporization is delta H of vaporization, or delta H of vape. That's how much heat must be absorbed to vaporize 1 gram of a liquid. So you're going to use heat of vaporization if you're vaporizing or boiling, and you'll use it for condensing as well, except you'll reverse the sign. Boiling and vaporizing are endothermic processes. Condensing is an exothermic process, hence the negative delta H. To calculate this, you'd have Q is equal to the mass times the delta H of vaporization. The first example is very straightforward. It says calculate the heat required to change an 120 gram sample of liquid ethyl alcohol into vapor at constant temperature. Now they may indicate what the temperature is, but you don't need the temperature in this formula because all it is Q is equal to the mass, 120 grams, times the delta H of vaporization. So in this particular example, very straightforward, Q is equal to the mass times the delta H of vaporization. The mass is 120 grams, and delta H of vaporization is 879 joules per gram. If this came up in multiple choice, the numbers probably would be a little easier to multiply in your head. We only want 3 sig figs here. We have 105,000 joules. The grams cancel. If this question was looking at the condensing of the substance, that is, for example, from vapor to liquid, then you'd have the negative of that value. Very straightforward, really nothing to it.
So we don't have the table anymore?
They're going to give it to you right in the problem.
That's easy.
Yeah, and so this you can see also in number 2 then, very straightforward. It says how much heat is released when 25 grams of steam at 100 degrees Celsius condense. That temperature is just the temperature at which condensation or boiling occurs, not relevant in the calculation. So how would you do number 2? Exactly, so 25 times negative 2,260, and that would be negative 56,500 joules. I can write that up. Is that going to be your question? Oh. Because you're condensing in this problem, yeah, when you go from steam to liquid. And you know heat's being released, and that's further evidence of an exothermic reaction.
So it would still be negative, even though it says how much is released?
The value actually, if they're asking for release, then you don't have to make it negative. If they just say calculate Q, then it's negative. So you're probably better off going with the negative and not making a mess. That's a sloppy parenthesis, sorry. Okay? Vaporization, boiling, condensing, all delta H of vaporization. All right, melting a little bit different. We're going to put this all into perspective because we touched on this in our intermolecular force, but we sort of brought, just swept it under the table. Now we're going to bring it back to life. And we're also going to connect all the dots because a few years ago, back in 2015, they really hit the kids hard with a question like this, and the kids who really knew what they were doing were able to put it together, but some of the kids just couldn't believe it was that easy, and they missed it. Melting, we know, is solid to liquid. Here we're going to use the heat of fusion, the delta H of fusion. This is how much heat is needed to cause 1 gram of a solid to melt into its liquid phase. So the only difference here is we're going to use the delta H of fusion compared to the delta H of vaporization. You use this for both freezing and melting. When you freeze, the delta H of fusion is negative. Calculate the heat required to melt a 25 gram block of gold. The delta H of fusion for gold is 64.5 joules per gram. So, exactly. And it's very straightforward. If you're not sure how to approach it, very often you can let your units drive your problem home. Here we're going to have Q is equal to M delta H of fusion. The mass is 25 grams. The delta H of fusion is 64.5 joules per gram. Cancel the grams. And you've got 25 times 64.5, 3 sig figs as such. Nothing to it. Very basic stuff that I'm sure most of you saw in honors if you covered thermo in any regard.
What is it, not only positive?
Yeah. Where'd I get the negative from? Me neither. Positive. Good catch. Positive times a positive is positive. I've been working on that with Sam. Has a little trouble with like negative divided by positive. That seems to throw her.
That's a negative, right?
Yeah. And a negative divided by a negative is positive, and a negative times a negative is positive. Math lesson of the day. Okay, the second problem says, calculate the heat required to freeze a 30-gram block of water into ice. So how are you going to approach that? 30 times negative, we've got it. So we have 30 times negative 334, and that's a mess. Here's where my negative comes in. Leave the desk alone, silly. So 3 ciggies, this is going to require, well, you could cheat a little bit. Could do that. Kind of nice, right?
Oh,
Yeah, or you could put it in the other. I adore you, but I don't trust you. Assault with a deadly water bomb. Okay.
We don't know what's inside it. So.
It's just water. I wouldn't leave anything but water there. Yeah.
You don't have to toss water to someone, but if you toss anything other than water, they could be allergic, which is harassment. If they are allergic, it's attempted murder. I know that because I watched a video of that.
Thanks for sharing.
It was like
Questions?
Oh,
All right. Yep.
so
and the
always
problem, would they ever give you like just fusion and then ask you about freezing?
Yeah,
They could do that?
absolutely.
You just switch the side.
Right. And they would do that. They wouldn't give you both.
Oh, okay.
Right. You just need to know one's the negative, the other. And then what they're also going to do to you, and we'll get to in a second, is it's not just going to be freezing. You might be cooling it and then freezing it. So that's putting pieces together. There's a multiple choice question in your packet, and we'll do one together also, because that's what they did to the kids. And they told us that was out of the curriculum years ago, and then poof, it appeared. I'm like, oh my gosh. Most of the kids could walk their way through it. I used to give it as an extra credit type question in honors, but then I sort of stopped, and boy, was I sorry. All right, so this is what you have seen previously. My little switcheroo is fast now, which is nice. If you watch the old videos, it's slow. Here's your heating curve. We've talked about this. For example, you have water in the solid state, that's ice. What can you say about molecular motion there? They're just vibrating in a fixed position. What do you say about intermolecular forces there? Very strong. What IMFs exist for ice? Dipole to dipole, LDF, and hydrogen bonds, all right? And we spoke about that hexagonal-like structure you have with ice, and that's why water, when it freezes, expands, which is different than most, okay? All right, here's the time required to melt 1 mole of ice. This is when ice and water are coexisting. What can you say about the change in temperature when you're undergoing melting?
Nothing.
It's 0. So here you can use Q is equal to MC delta T to calculate heat transfer. Here you're going to use Q is equal to M times the delta H of fusion. You've got it, and you may want to scribble that in. So here you have water in the liquid state. The IMFs have partially broken down, so they're not as extensive. It warms until it hits 100 degrees Celsius, and then the temperature is constant because this is when the substance is undergoing a phase change. Water and steam are coexisting. Here would be the delta H of vaporization. So with delta H of vaporization, also what you will see if you were, and I think this is in the other room already, if you were to look at if you were to look at the delta H's of fusion versus vaporization, what could you note in regard to these quantities? If you compared copper, which is greater, delta H of vape or fusion?
Vape.
And do you see that consistently throughout?
Yes.
So what does that say?
Takes more energy.
It takes more energy to vaporize a substance than to melt it.
Yeah.
Why?
All the
You got to break all the IMFs. You got it. And that sometimes comes up. All right, and so this says what happens when a substance transitions through different regions. I believe you have this in your notes. It's in your practice quiz,
Yeah.
which you got the other day, so that's why I took it out of the notes, because it just was taking up too much space, but you have it. So let's take a look at this one. It's in your notes. I took it out of mine.
So we haven't even
When you snip things, it really gets sloppy. Like they need a better, you guys probably know like a better tool. Like I snip things, so I snip it out and I pop it in somewhere else, but you lose resolution and there's got to be a better tool to cut stuff out. You can't always copy and paste, you can snip. So I don't know. I wonder if the resolution there would be better. It'd be, it's like pixelated, yeah. All right, one of you figure it out and let me know. Here we go. 1 cup of ice has a mass of approximately 250 grams. The ice is at 0. How much heat is required to melt the ice and then warm it to 25 degrees Celsius? A table of useful information is provided. You want to try it yourself first?
Yeah.
All right. I'm going to try it too. In pencil. Watch your units in this one. They kind of give it to you really meanly. And I really feel like this is a calculator problem. The numbers would have to be nicer.
So we can.
Yeah, go ahead. It'll be easier for you.
That's where I messed
Got it.
up.
I'll give you time. No. But if you have kilojoules per kilogram,
Yeah, that's right.
the kilos cancel. So that's the same in joules per gram, right?
Mhm.
Did you see it? You could have just canceled kilo on both.
Yeah.
That's the best approach there.
But it's in grams for double thing?
Yeah.
Okay.
And that's because the specific heat is typically in joules per grams degrees Celsius.
Oh, okay.
Yeah, yeah.
Thank you.
Oh. I didn't know if you wanted me to show it yet. And so that's closest to D. Did you get it?
No.
You just do both pieces and add them together, see?
That's fine.
Oh, I used to work for them.
Yes, yes? Okay. And the other thing that I wanted to show you, because part of this came up one year, although in your POGL packet I've got a good one there too. Bomb calorimetry's out, but before we go there, see it says APC exam 2005, number 7.
2015.
Say it again.
2015.
What did I say?
2005.
I lost 10 years. I can make it bigger, right? Okay. So, here was the very last question back in 2015 on their exam. All right, let's read through. Aluminum metal can be recycled from scrap metal by melting the metal to evaporate impurities. Calculate the amount of heat needed to purify 1 mole of aluminum, originally at 298 Kelvin, by melting it. The melting point of aluminum is 933 Kelvin. The molar heat capacity of aluminum is 24 joules per mole Kelvin, and the heat of fusion of aluminum is 10.7 kilojoules per mole. Now this was difficult for the kids on a lot of levels. First of all, you had moles and you had Kelvin. The Kelvin's irrelevant.
You convert the grams, right?
You don't even have to convert. It's just a matter of working through the problem and letting the units drive you home. So what do you think you want to do?
5 grams.
Yeah.
I wouldn't even bother with grams. Keep it simple. All right, this is gonna be a little hard because you don't have it,
Yeah.
but let's pull the relevant information out together. It says,
But you put it up, and then you write it, and then we go from there.
say it again.
You show it up there, pull the relevant information onto there, and then switch.
Yeah, I'll read it and we'll pull. I'm trying to think how to go back and forth. I wish I had actually just snipped it right into your notes so you had it.
No, I'm saying you leave that up there until you're done writing it down, and then you switch onto that.
You just want me to write it down as we go? And you want to see the question?
Well, until you have it written down, then when you have it written down, go from there.
Okay, sounds like a plan. We have 1 mole of aluminum, right? So I'm writing N is equal to 1.00 moles. The initial temperature TI is 298 Kelvin. I'll split screens, I'll flip and let you copy if whatever's easier for you. The melting point, so that's going to be the final temperature, is 933 Kelvin. The molar heat capacity, that's capital C, is 24 joules per mole Kelvin. And the heat of fusion is 10.7 kilojoules per mole. In hindsight, I do wish I had snipped this. Have you ever seen this? This is so cool.
You've done that before.
Ah, it is cool.
We're not doing part B.
I'm not right now.
Can you edit it from there?
And I will tell you that when you snip stuff in, it's better to do, I'm actually,
A text box.
yeah,
You love your text box.
I do. So I showed you this too.
Yeah.
I showed you everything. It's time to graduate. Not today, fresh one. Isn't that beautiful now? And then if you don't like that little box, you can dump it. Do we want it or not want it?
No.
I think we kind of do want it. I disagree. Sort of highlights it. All right. So here we go. We want to calculate the amount of heat. So we want to calculate Q. This will be for warming it up. So we know that Q is equal to MC delta T. But this looks a little different. But let's make it easy.
You were given C, right?
Yes.
Yeah. So
We're going to leave the M open right now. This is a big C. If it's not clear, I'm going to make it a big one. Because that's heat capacity, not specific heat capacity. And that's 24 joules per mole Kelvin. And delta T is, this is calculator based, 635, not that you couldn't do that in your head, Kelvin.
wait, so the big C you can put in for the little C?
As long as you put moles here.
Oh, okay.
And this was 1 mole, right?
Yeah.
Oh, so they gave it to us in joules per
So
mole.
you're trying to let your units.
So I'm letting my
Yeah.
units drive me home. So 24 times 635 is 15,240 joules. That's a not so nice 5, so may not be clear. And with sig figs, you should be at 15,000 joules. And you also have some kilojoules floating around here, so if you want, make it 15 kilojoules. That's the first part. What else do you have to do?
Add the
Diffusion.
You got to go with the fusion piece now. And usually it's mass times delta H of fusion, but when you look at the delta H of fusion, that's 10.7 kilojoules per mole. So we've got to have, just leave it in moles. That's why I said you don't need to start converting. Let your units drive you home. And what's the last thing you need to do? So you would have 26 kilojoules. Okay?
Can I see the question with you?
Absolutely. Question?
Yeah, the question.
Oh, yeah. I'm going to flip back to the question. We actually can do B also. It says the equation for the overall process of extracting aluminum from aluminum oxide is shown. Which requires less energy, recycling existing aluminum or extracting it from aluminum oxide?
What does it mean by recycling?
The first one,
Oh, so you're gonna do the same thing for B?
no, you already did it, didn't you? So we're just asking you to compare those two quantities. You got 26 kilojoules versus 1675.
I'm gonna go with the answer.
Yeah.
This one's
Recycling.
The only thing
It's just kilojoules per mole.
is that you have 2 moles here. So you would divide that by 2. Yes? But it's still much, much less by method A. Let's look at the scoring guidelines there. See what they came up with. We were correct right here. And that was a 2-pointer, right? Pretty easy. And then, like I said, you had to divide by 2 here. And now you can see clearly. And it didn't require all that much, but the kids were just dumbfounded by the first part. And this question, I have to look at the percentage, but nationwide this question was a big, big bomb. Globally, I'll look up the global thing afterward. I don't think I have it downloaded. I have to go to the site, but I can grab it.
Is there gonna be a question up here where we won't know the answer? Like one of the free response?
What do you mean you won't know the answer?
Like for stats, one of the free response was supposedly a question we didn't learn. Like, it was supposed to happen.
You didn't learn because you didn't get to it, or you didn't learn because it wasn't in the learning objectives?
Yeah.
Everything will match a learning objective, and I go through all the learning objectives. At the very end, once I'm done teaching, I march down, I'm like, got it, and if there's something I feel like we didn't hit well, we come back to it. There's always a couple questions, like remember I used the word dimerize and I sort of threw it at you, but I didn't elaborate upon it. So there'll always be a few questions where you'll be like, I'm not sure where this is going, but I think you'll feel very comfortable when you walk in and walk out that you were prepared well, you studied well, and that you did very well.
We have psych the same day.
Some of you, I guess, do. Who's in psych? Oh, that's a lot. Have fun, guys. We'll talk about that later.
Psychology isn't bad though.
Yeah.
But it's still another 10.
You'll be fine. All right, couple things I want to finish up before the break. Bomb calorimetry we no longer assess, although interestingly it's sort of set you up nice, but we don't do it anymore. So we're not going to deal with it. And then I do want to get into Hess's Law. This looks nasty, but it's really pretty easy once you get the hang of it. All right? Yeah, you got to flip and multiply and add. It's not difficult.
Is this like the reaction mechanism kind of?
Kind of. Yeah.
But it's break time, you said?
Not yet. We didn't get started on time, so we're going to get through Hess's Law before we break. All right. With Hess's Law, sometimes you can't get delta H of a reaction by doing delta H's of formation of products minus delta H's of formation of reactants. Sometimes you're missing pieces of the puzzle. So use a different method. I'll come back to the slide in a sec. You can use what's known as Hess law to determine the delta H of the reaction, and the way that you approach this is that if you can sum equations up to a net equation, then to get the delta H of the reaction, you simply sum their individual delta H's. Couple of rules. And a lot of you are seeing this, you're like, oh, I remember this. Some of you have never seen it, and it's not difficult. If an equation has to be reversed in order to get them to add up, then you simply change the sign of the delta H value. If an equation has to be multiplied by some factor, it could be a fraction or a whole number, then you multiply the delta H value by that factor. Let's take a look at the first one. Very, very easy once you get the hang. If we go through this and you don't feel like you've got it, I'll go back to the honors notes that are broken down a little more simplistically. It says use the following equations to calculate the delta H value for the reaction in bold. So we want to know the delta H for this reaction. We're given two other reactions and we're given their delta H's. So everything in black here is given, the highlight wouldn't be. Sometimes they don't have this at the bottom, they have it over here. I need to see if that when I add these two equations, they equal that. And I can see that they're not going to. Because first of all, nitrogen dioxide in the net equation is a reactant, where here it's a product. And that suggests to me I need to flip this equation over. So when I reverse the equation, I must reverse the sign. And that is shown here. So I reversed the equation here. I made nitrogen dioxide a reactant, nitrogen gas and oxygen gas now are products. Now I see if I can add these two equations together to equal this. Listen. If a substance is a reactant on one side of the equation and a product in a different equation and their coefficients are the same, they cancel. So nitrogen gas cancels, the 2 moles of oxygen gas cancel. If this was a 2 and this was a 1, I would do 2 minus 1 and I'd keep an oxygen over here, and we'll get to that in a bit. So now if I add these two equations together, that drops down, that drops down. When I flip this equation, I'm not sure why that arrow's there. I think it's just a typo. Oops. Sorry. That's when I change the sign. And now I take the sum of the delta H's and I get negative 24.0 kilojoules. Now, at your level in the multiple choice, sometimes these numbers get hairy. And to keep it easy, very often they'll leave X's and Y's in and something easy. And you'll see that in the multiple choice much easier than dealing with numbers. Let's look at some additional examples. This requires practice. At the end of your chapter, you'll get a lot of it. You've got to do a few. I'll give you something crazy hard today to do. If you can do it, that's a good sign. It requires practice. On my honors page, I do have a whole worksheet on this. I can stick it on your page if it's easier. All right, let's take a look. I feel like this is the same problem. It is. Don't know what happened. In the first one there, you can see that you've got in bold 2 moles of carbon in the graphite form reacting with oxygen to make carbon monoxide. And there's several things I want to show you. One of the key questions that kids ask, where do we start? I look at the first reactant. I see that I've got 2 moles of carbon. I find it. I see that carbon's right here, so it's on the correct side, so I don't have to start flipping equations, but I don't have the right number of moles. So I have to multiply this whole equation and the delta H by 2, which I do here. 2 moles of graphite, 2 moles of oxygen, 2 moles of CO2, and I multiply this by 2. And I hope this isn't confusing. You'll either get a quantity or you might just get an X. All right, multiplied by 2. And I only called this negative X here because it was XO. Now I'm going to look at the other piece, and I don't know how to get rid of that lightning bolt. So now I'm here, the only thing I did was multiply that. I guess I flipped it. All right, so all I did here was multiply by 2. So I have a 2, a 2, and a 2. Oxygen's sort of all over the place. I don't want to play with oxygen right now. I see 2 moles of carbon monoxide. Where do you see carbon monoxide? Here. Does the coefficient match? Yes, I'm not going to have to multiply it at first glance. But what do I need to do to this equation? Flip it over, and what do I do to the sign? I change it, so I make it positive. And I'll walk through this one with you from scratch so you can see it piecemeal. And that's what I'm showing here. This has been flipped, and this is positive now. Now I look to see if these 2 equations sum to this one. The graphite drops down, the carbon monoxide is here, and here's where I have 2 moles of oxygen on the left and 1 mole of oxygen on the right. If they're on opposite sides of 2 different equations and the coefficients differ, whichever side had more initially will keep the substance, hence on the reactant side, and you subtract. 2 minus 1 is 1. If the oxygen was on the same side of the equation, you'd simply add them together and keep them on that side. And now you sum these. So you've got 2 times negative 390 or so plus 566. Exothermic reaction. Let's walk through this one very carefully, and hopefully you'll be good to go. And then I'll give you a hard one, and then we'll take a break.
Is this one the hard one?
This is easy.
No,
This
this
is
one.
from honors. The one that says crazy hard?
Yeah.
Well, duh.
Well, I don't know. It
Silly.
said number 112, so I don't know if that's in the book, and you just gave another example.
I don't know, JJ, have you opened the book yet?
I'll explain what I've written there. We should be nicer to each other, though. Okay. Very often when I give you these types of problems, I'll separate it out nicely so you can scribble in between. Like I dropped everything down, but I would just write a top. But I'll show you what I mean right here. So this one is negative 2219.9, and this is negative 283.0, and the net equation is C3H8 plus 7 halves O2, yielding 3CO plus 4H2O. And I'm going to show you how I work it piecemeal. For those of you who are like, I remember how to do this, I don't need you, that's fine. Just give it a shot on your own. But some of you have never seen it before, so I think you may want to watch. I look at the first reactant, and I see it right here, suggesting that the first equation is written in the proper order and the coefficient is right. It's not going to need a sign flip. It's not going to need a multiple. The oxygen's all over the place. I don't want to play with it. I see 3CO. Well, that's here. So what do I need to do to this equation? I'm going to flip it. I'm going to get CO2 yields CO plus 1/2 O2, and when I flip it, I'm going to change the sign. So it was negative, and usually with a negative, I just slash it and make a positive. But I'm not done yet, because the coefficient doesn't match. So what do I need to multiply this by? So I'm going to put a 3, got to do it to all of them, and this becomes 3/2, right? That's not going to work so well. And so when I multiply those by 3, I multiply this by 3. And now I'm going to see this correct. This correct. The oxygen's a little tricky.
Just do 10
You have
over
5, which is 10 over 2. If you want to think of it that way, it's going to be easier. 10 halves minus 3 halves is 7 halves.
Do you put over there because the coefficient on the left side is greater than
Exactly. Absolutely. And then you sum this. So you have negative 2219.9 plus 3 times 283 is negative 1370.9 kilojoules. Exothermic reaction. And what I'll have you do prior to taking a break is this one. The reason why it says Z number 112 is it's number 112 in your textbook, which is Z and Z.
Why do those?
This one's kind of,
Yeah,
this is a little bit of a stinker. If you can do this, you're golden, and you probably never see anything so hard.
This is ridiculous.
So we'll take a break. I'm going to split the film. At this point, you should feel pretty comfortable with Thermochem, Q, delta H, etc. And we're going to link this all together to the bigger picture in the next chapter, which will start in a little bit.